We have a couple examples of working with the washer method. Suppose our region is bounded by these two functions. Region is bounded by y equals 4x minus 3 and y equals x squared. Now I have drawn the pictures here, and anytime you need this, I will play the role of a computer. You can draw these on a calculator or a computer, whatever. I will give you the picture of this basic region. I will sketch that graph and provide that for you anytime you need that. Anytime I ask you to do this process, I will provide this picture for you. What might not be obvious here is where those curves intersect. All we need to specify is this, because if we have that fence, that region is bounded by those two curves. The idea is if this were fenced in, the horses couldn't get out, or however you want to say that. And so this region is bounded, but the question is, if we're going to do this process, we need to know what is the partition. All right? Well, if we're going to revolve about the x-axis, and if we're going to use the disk or washer method, revolve about the x-axis, then the axis of revolution is the axis of partition. So if we're going to use that method, revolving about the x-axis, part A, part B is revolve that same region about the y-axis. So part A is take this region, revolve it in 3 dimensions about this axis. You're going to generate essentially what's going to look like a tulip, the flower. Right? This is going to be a tulip flower because it's going to be this piece and it's going to be hollowed out in the middle. If one of the boundaries, or let's get it this way, if the axis is not one of the boundaries, then you're going to generate this hollowed out region. If instead of this region, suppose instead this bottom parabola had not been given, suppose we're just simply given the line, this side, and if the axis is one of the boundaries, then we have this entire solid region, and then when we rotate this, there will be no hollowed out portion. So that would not require the washers. In this case, the x-axis is not one of the boundaries. The axis of rotation is not one of the boundaries. And so if we rotate this, there will be this hollow piece. That's always going to be the case. If the axis of rotation is not one of the boundaries, then you will have this hollowed out phenomenon. If the axis of rotation is one of the boundaries of the original region, then when you rotate, you will not generate this hollowed out region. So that's how we know this is going to be washers and not discs. All right? So the only thing we need to know for the washers is if this is the axis and we partition this. Now, here we know. We're going to partition this axis. We need to know where to start and we need to know where to finish. Those values are required because when we make this integral, the integral is going to have those values as the limits of integration. If those are not explicitly given, then what you would do is find where these two curves intersect. In this case, and any case that I would ask of you, typically those values might even be given, because that's not really the point here. But what you could do to find those is just set these two functions equal to each other. Set these equal and solve that equation. And if you solve that equation, it's not very hard to see. You get x equals 1, you get x equals 3. So I'm going to trust that you, if that's going to be required of you, I'm going to trust that you can handle Algebra 2 from high school. So he said in sort of a passive-aggressive way. But yes, you should be able to find that this is 1 and this is 3. So now we know the limits of integration. All right? So we know we're going to rotate. We know the axis of revolution. We know this is the washer method. And so we know the volume is given by pi. The pi comes from the fact that we're rotating. That's the pi times the radius square from the area of the disk, of a circle. So now we need the limits of integration, which we just found. 1, 3. This is not guesswork. You can cobble this together. You know we need, and you know this because you can have your notes with you. You know we need outer radius. All you need to know is, if we're rotating this, which is the outer radius? The outer radius is top The inner radius is bottom. It's always outer minus inner. It's always top minus bottom. Top minus bottom. Or if you will, furthest minus closest. Furthest minus closest. It's the outer radius minus the inner radius. So the outer radius is given by 4x minus 3. I'll need a little more space here. Quantity squared. Minus, I need the inner radius. Well, the inner radius is easy. The inner radius is the parabola. It's squared dx. And if all you're asked to do, all I'm going to ask of you is to set up the integrals. That's all you need to set up. Now, this would not be very hard to do because that's square that out and add the terms in. That's just a power rule integral. This is a calculus 1 integral. The computation is what I'm after. The setup is what I'm after here. So set up the integral that finds that volume. So there's our integral for number 1. All right, number 2. Same region, but now we're going to revolve about the y-axis. And we haven't explicitly done this, but I think it should be pretty straightforward. There's the straight line. There's the parabola, at least conceptually. This is 1, and we know what these points are on the y-axis because we know what the function values are. If this is 1, we just know this parabola. This is y equals x squared. And this is y equals, what is that, 4x minus 3. This is 1, comma 1. If this is 3, the parabola tells us this is 9. Now, suppose we're rotating about the y-axis. We're going to revolve about the y-axis. The axis of rotation is the axis of partition. And the axis of partition gives us the variable of the integral. So the volume is going to be pi times whatever it's going to be dy. And so we need outer squared minus inner squared, dy. And all we need to do is find the outer minus the inner. And what we may not do is, and when we rotate along the horizontal axis, the outer is the top and the inner is the bottom. But notice when we rotate about this vertical axis, the outer radius is the rightmost. The inner radius is the leftmost. Larger distance minus smaller distance. It's larger radius squared minus smaller radius squared. Right minus left, just like it was top minus bottom. Larger distance minus smaller distance. And so the parabola is now corresponds to the larger radius. The line now corresponds to the smaller or the inner radius. But notice, the outer radius is the parabola. What I may not do, is it clear? I may not write this as x squared. That's the wrong variable because this needs to be a y integral. If we partition the y-axis, every variable in here needs to be y. Which means both of these equations, you need to back solve them to make them functions of y. That's not very challenging. In this particular case, if I back solve this, in fact, I can just do this up here at the top. If you back solve this, this is y plus 3 all over 4 is equal to x. Add the 3, divide the 4. It doesn't matter what it looks like, just solve for x. And then this is really straightforward. This is the square root of y is equal to x. So if they're functions of x and you need them as the function of y, you need to swap. And so in this case, we do not use the x squared. This curve is now given by the square root function. This curve is still the line, but it's given by this linear function instead. So outer radius is the parabola. That's the square root of y. Inner radius is the line, which is the y plus 3 all over 4. And the nice news is you don't need to simplify it. You don't need to make it look nice. Just find the integral, put a box around it like you're proud of it, and you're good to go.